questions? Oh, you were talking to him.
So
And-
on Thursday, that's the concept test, is that, like, what chapters does that cover? Just what we learned after this?
So tomorrow is the calculator test, we got the 2-hour block.
Yeah.
Thursday is that multiple choice test that you took, the first day or so.
Oh, okay.
It
I see.
it basically is through chapter 6.
Okay.
Any other questions? All right. Any other questions? We last left off. We had particles in a box. And the side that we're concerned with at the moment has an area of A, and the only particles that can hit the box within a certain amount of time are those in the shaded region. And what was the last formula I put up on the board?
I've written down J of wall equals N over V, Vx, dA. 2 then Vx.
All right. You have impulse on the wall is what?
N over V times Vx times T times A, parenthesis 2M Vx 1/2 in parentheses.
Good. That looks like a Y. It's supposed to be an X. Oh, okay. All right, so that puts it. So I got the 1/2 Henry X, 2 Henry X, I think up here. All right, what is impulse?
Impulse.
There are 3 answers I will accept.
Has something to do with momentum.
Okay. 5 marks.
The change in momentum.
Ah, there's 1. All right. Two to go. Or actually 1, really, but there's another answer I would accept.
Force times time, or.
There we go. Those are the 2 physics ones. The other one I would accept was when someone suddenly buys a flash. All right, so we have this is therefore equal to, we got to this from the change in momentum aspect of it, looking at the impulse on a particle, and that must be the negative of what the particle exerts on the wall. So that should be the sum average force times time. Obviously, we can get rid of delta T. So we now have a force acting on the wall, or an average force. So N over V, Vx. The 2 and the 1/2 cancel out. I'm left with A at the Vx squared, M. Take a moment to make sure that there's not a careless error there.
What happened to the 2 and the VX?
That 2 cancels out with that 1/2, and those 2 VXs combine to get VX squared.
Yeah.
All right, this is an average force, where we can simplify it, just assume that all the particles have the same mass. We're assuming uniform particle distribution, and we've got some area A that's being hit. This Vx here, we're sort of working on this from as if things are just hitting one wall here, but it is a 3-dimensional problem. This is an average here, so we have, because that's an average force, and make it more explicit over here. And the 2 brackets there is yet one more way of indicating average. The 3 ways of indicating average for something: that, AVG, or that with a bar over it. Those all mean average.
And why is that important to specify?
Just because I don't think I've used that notation before.
Oh,
And for whatever reason, that was my mood. All right, so if we have particles actually traveling in 3 dimensions, I know that its velocity is, assuming traditional, Vx I hat plus Vy j hat plus Vz k hat, assuming I hat, j hat, k hat are in the x, y, and z directions respectively. If I get a dot product with itself, I end up with v squared is equal to vx squared plus vy squared plus vz squared. This is v dot v. And if the particles truly are random in there, moving in some random direction, if I look at the average value of v, well, that should just be the average value of vx, sorry, the average value of v squared. It's the average value of vx squared plus the average value of vy squared plus the average value of vz squared. All right. And if it truly is random, then the average value of Vz, the average value of Vz squared, the average value of Vy squared, and the average value of Vx squared should all be the same. Because again, there's no reason to give any preference to one or the other. So the average value of V squared would just be close enough to the average value of Vx squared divided by 3. That is a mistake. 3 times Vx squared. In other words, Vx squared, the average value of Vx squared is 1/3 of the average value of V squared. So add N over V M 3 V squared.
So, what would you say is the best notation to differentiate between volume and velocity?
I try to, obviously it's not 100%. For volume, I typically put the serifs at the top, or I try to put the serifs at the top. And then the other one should be a lowercase v, and when I'm thinking about it, I put the little flare at the end to indicate speed.
And this is speed, not velocity.
At this point, it's speed.
Okay.
That's velocity, but what we did the dot product with itself, it's a scalar product. Other questions at this point? All right. So let me just divide area, both sides by area. So I get F, the force divided by area. And actually, at this point right here, there really should not be a vector symbol over F.
Why?
Technically, yeah, my notation got sloppy here. This should be not this implies the total force. We're only looking at the forces in the x direction, so it's really just the x component of the force. And at this point, this would be just the average force. Because I have vectors on the right-hand side in this equation, so there shouldn't be one on the left-hand side.
And so using the same logic that you used to say that, okay, we can just use v squared f or x, or vx squared, can we substitute and use vy squared or vz squared?
Yeah, I'm making the argument that with random particles moving in random directions, the average value of Vx squared, average value of Vy squared, and Vz squared are all the same.
Okay,
So that's why I have 3 times one of them squared.
got it.
Because I started out initially looking at just Vx,
I see.
that's why I stuck with Vx.
Got it.
But we could have done the same argument with everything hitting, any of the other surfaces.
Okay, thank you.
So a force divided by area is equal to the total number of particles divided by the volume, in other words, the number density, times, actually I'm gonna put it in the slightly better, more traditional notation. I got 3, typically the numbers come first, N over V, number of particles per unit volume, times M V squared. Now at this point, some stuff should look somewhat familiar. Where have you seen MV squared before?
Momentum.
Kinetic energy.
That's the one.
Darn.
You might have seen it with momentum because we did in perfectly elastic collisions, it shows up. But
That was 1/2 O and v squared, there's the v squared.
all right. So we're dealing with a gas here. Why not just make it ideal? We're just doing a sort of a crude estimate. There's a much more formal way of deriving this, which is tedious and gets you to the same spot. What's the ideal gas law?
So,
All right, let's see if we can narrow that down.
Ideal gas law.
Yeah.
I have it in my chemistry notebook. What's that called? Don't bring chemistry into a physics.
But you can't help but bring physics into a chemistry class.
Indeed, so. Indeed, so.
All right, ideal gas law. There's 2 versions of it. PV equals nRT. Does that ring a bell?
Yes.
So look, I got a couple knots there. What is N?
The number.
Some.
All right,
Number of
Again.
particles.
number of what?
Number of particles.
Number of particles typically is a capital N, it's a lowercase n. Everyone's favorite root.
Newtons.
What?
Squirrels.
Mole.
It's the number of moles. What's a mole? The chemistry version, not the animal. Although if you're interested, if you enjoy What If you haven't read it or heard it or seen it, he does talk about what would happen if you had a mole with moles. But anyway,
Is it shuffle molecule?
it is not.
It's a substitute for a really, really long number.
Yes, that's what it is. A mole is just a number. 6.02 times 10 to the 23rd. It has no units, just like a dozen is 12, score is 20. A mole is 6.02 times 10 to the 23rd.
Is it 23?
That's a 23. So it's just a number.
Okay.
So if I had stuck with the SI units, and if you asked me how many tests we're having this year, I could have done it in terms of number of moles. R. See, chemistry had a huge impact in your lives. Yeah. Ideal gas constant. All right, not asking for, well, yeah, I am still asking. Capital T?
Temperature.
Yes. In the absolute scale. P? How about V?
Volume.
All right. And P?
People, no.
How many of you have had chemistry?
High school.
Yeah. And are not afraid to admit it? So there are at least 4 of you, I think. 5, 6, or is that 5.5?
I've only taken.
I do remember seeing this equation though, and then E was something.
That begins with a P, just as a hint.
Is it pressure?
Was it?
Pressure?
Yes, pressure. And despite what my daughter's chemistry textbook said, pressure is not a force.
What's that fit every gas?
Pardon?
What's that fit every gas?
Constant, ideal gas constant. All right, this is the ideal gas law. This makes the assumption that the particles are point particles. They do not interact with each other. They will interact with the wall, but they do not interact with each other, and they have no size. If you throw in a little bit of reality, then you can get into van der Waals equation, which brings into the fact of size, and maybe the fact that they interact. I can't remember that part. All right, so this is a, I was about to say rather critical chemistry equation, but I haven't had chemistry since the early 80s, so I could be off on that one. There is a physics version of it, which doesn't deal with moles. I generally start with this one just as a way of connecting what we're doing now with what you've done in the past. The physics version doesn't look at the number of moles, and it takes basically these two right here and looks at the number of particles and a different constant. So number of moles times the gas constant is equal to the number of particles times Boltzmann's constant.
You said, what's his base constant?
Boltzmann. Yeah, named after the Boltzmann. Yeah, I think there's only one family really that if you give the last name, they could stand for several of them. Bernoulli's the only one. There's several of them who are famous. But until a couple of years ago, I assumed they were all the same person. All right, so number of particles times Boltzmann's constant is just the number of moles times the gas law, or the gas constant. So, and the reason I'm making that switch there is that we have a capital N right here, which makes life a little bit simpler. Now, thinking a little bit more into this, pressure. What is pressure?
It's not a force.
That is correct.
It's a limited space. Cause like, I understand that when there's particles in a box,
Okay.
and you decrease the volume, pressure increases because they're hitting it a lot more frequently,
Okay.
because they don't have space to move.
And that also is sort of built into this. If the temperature and the number of particles inside stay constant, then as volume goes down, pressure has to go up. They're inversely proportional. All right?
So pressure being the inverse volume,
No,
the inverse.
no, that doesn't quite work that nicely. Inversely proportional, not inverses of each other.
I used to categorize it as pressure, how much force you're putting on something. Now I know that's not it.
So, anyone seen the person lie on a bed of nails? Okay, how do they do that? I mean, besides lying on a bed of nails, why are they not killed by it? Or badly wounded?
Pressure is evenly distributed.
Not the pressure evenly distributed.
Right.
Say again?
The weight, just,
All right, so you get weight, or more specifically, the normal force the nail exerts on the person. Basically, the force is distributed evenly. So if I just had a nail sticking right up and I stepped on it, as unfortunately I have done, not as part of a physics experiment, what would happen?
it'll go through too much force.
Yeah, I have a whole lot of force in a very tiny area, whatever the tip of the nail is. But if I spread it out, so I'm not putting all my force on the one nail, but spread my weight out over a bunch of nails, then I can get on it without it puncturing my skin.
Mind you,